Some nights deliver their wonders in a hush, and others arrive with fanfare, bright, undeniable, impossible to ignore. The Northern Lights are neither of those, really. They are not a single moment you can schedule, and they are not a single destination you can point to on a map and declare solved. They are a working relationship between the sun and earth, between motion and restraint, between an invisible field and a thin layer of air that can be persuaded, briefly, to glow. They are defined as much by limits as by action, because the aurora is not the sun doing something in isolation, it's the sun sending a stream, and Earth deciding, quietly, continuously, how much of that stream is allowed to couple in, where it will be guided, how it will be stored, when it will be released. The light we see is the last step in a chain of bookkeeping. Energy arriving, energy routed, energy transformed, energy spent. A ledger balanced in photons. If you could follow the whole system with your finger, if you could trace the path from the solar wind to the polar sky, you would find no single switch that turns the aurora on. Instead, you'd find a set of conditions, a set of boundaries, a set of pathways, and a set of release valves. You'd find a kind of infrastructure, and tonight we'll follow the evidence gently, one calm detail at a time. Back in my office, it's quiet, but the silence isn't empty. It's threaded with the faint purr of power and ventilation. A desk lamp warms a folder labelled Northern Lights/Aurora Borealis, the kind of label that doesn't promise spectacle, just a phenomenon that keeps happening in its own time, whenever the conditions line up. Outside the window is a dark slice of sky, and inside the room, everything feels like a small model of what we're investigating. Quiet inputs, controlled pathways, steady constraints, and the occasional bright consequence of a system doing exactly what it was built to do. My office has boundaries the way Earth does: walls, a window, a door, rules about what gets in and what stays out, a mailbox for incoming information, shelves for storage, a desk surface where I sort what matters from what doesn't, a lamp that turns electrical power into warmth and light, right here where I can use it. The aurora, strange as it seems, has all of that too. Not wood and paper, but fields and plasma. Not shelves, but reservoirs of energy in a stretched magnetic tail. Not a lamp, but a layer of atmosphere that can be excited to shine. So, settle in. Let the room soften around the edges. Let the folder open without urgency. My name is Madeline Rowe, and tonight's case is focused on the science of the Northern Lights. And if you'd like more calm case files like this one, you can subscribe, so these investigations find you easily the next time you need a quieter night. Okay, now let's begin. The first thing I do with any case is define the scene without romance. Not because romance is unwelcome, but because it can blur the edges of what's real. And the aurora is real in the most satisfying way. It is light with a cause. It is motion you can't see, made visible at the end of a long chain of interactions. An aurora is produced when charged particles, most often electrons, enter Earth's upper atmosphere and collide with atoms and molecules there. Those collisions transfer energy. The atmospheric particles become excited, which is a precise word that means their electrons are pushed into higher energy states. And when those excited states relax, when they fall back toward lower energy, they emit photons, light. Not metaphorical, actual. That's the last step, and it's the one our eyes can witness. But to understand the aurora the way a careful investigator would, we have to follow the chain backward. Where do the charged particles come from? How do they reach Earth? Why do they concentrate near the poles rather than falling evenly across the planet? What decides the colour, the shape, the timing, and the suddenness? This is where the case gets quiet and technical in a soothing way, because the answer is not one thing, it's a system. Start with the sun, not as a disk of light in the daytime sky, but as a star with an atmosphere so hot and restless that it cannot help but leak. The sun's outer atmosphere, the corona, streams outward as a flow of charged particles threaded with magnetic fields. This flow is the solar wind. The solar wind is not a single gust, it's a continuous outflow, variable in speed and density and magnetic orientation. Sometimes it is calm enough that Earth's magnetic shield deflects most of it with minimal fuss. Sometimes it carries structures, compressions, rotations, clouds of magnetized plasma that change the accounting. Sometimes it arrives fast, sometimes it arrives slow but persistent. And sometimes the sun sends a more dramatic parcel, a coronal mass ejection, a CME, a large cloud of magnetized plasma that can disturb Earth's magnetic environment when it arrives. But even then, Earth does not simply get hit and glow. Earth responds, and that response is shaped by the magnetosphere. If you've heard the word magnetosphere before, you may have pictured a neat bubble around the planet. That's not wrong, but it's incomplete in the way a simple floor plan is incomplete if you're trying to understand how a city works. The magnetosphere is a region of space dominated by Earth's magnetic field. It is carved into shape by the solar wind like a steady current shaping a coastline. On the day side, the side facing the sun, the magnetosphere is compressed. On the night side, it is stretched into a long tail, the magnetotail, extending far behind Earth in the direction away from the sun. This matters because the aurora is not just an atmospheric phenomenon. It is the visible footprint of a much larger process, energy transfer from the solar wind into Earth's magnetic environment, and then into the upper atmosphere. In my office metaphor, the solar wind is the incoming mail, constant, sometimes routine, sometimes urgent. The magnetosphere is the mailroom plus the security desk plus the building's internal routing system. Most of what arrives is deflected, routed around, sent away without entering the building, but some conditions allow energy and particles to couple into the system, and when they do, the building doesn't collapse into chaos. It processes. A key idea here is that magnetic fields can store energy and can be rearranged. When the solar wind's magnetic field and Earth's magnetic field are oriented in a way that allows it, they can connect through a process called magnetic reconnection. Reconnection is often described dramatically, but at its heart, it is a change in the connectivity of magnetic field lines that allows energy to be converted and particles to be accelerated. Think of it as a locked door that sometimes becomes a revolving door. Not always, not at will, only under certain conditions. When it happens, energy that was carried by the solar wind and held in magnetic configurations can be transferred into Earth's magnetosphere. Once energy enters the system, it doesn't distribute evenly. It follows pathways. In a magnetized plasma, charged particles tend to spiral around magnetic field lines. The field lines become guides, rails, if you like, along which particles can travel. And Earth's magnetic field lines converge near the polar regions. The geometry makes the poles a natural place for particles to funnel downward into the atmosphere. This is why auroras tend to occur in ring-shaped regions around the magnetic poles, called the auroral ovals. They are not perfectly fixed rings. They expand and contract depending on geomagnetic activity. During quiet times, the oval stays tucked up at higher latitudes. During strong geomagnetic storms, it can widen and shift equatorward, letting people much farther from the poles catch a glimpse of the phenomenon. If you've ever heard someone say, with mild disbelief, that they saw the northern lights from a latitude that shouldn't see them, what they're really saying is that the oval expanded enough to include their sky. And now we can return to the atmosphere, but with context. The upper atmosphere is not a single layer. It's a set of regions defined by density and composition, and how strongly they are ionized by solar radiation. The aurora tends to occur in the ionosphere and thermosphere, high enough that the air is thin, but still thick enough that collisions happen. The typical visible aurora occurs roughly from about 100 kilometers up to several hundred kilometers, depending on conditions and the type of emission. At those altitudes, oxygen and nitrogen are the main actors in our color story. Oxygen can emit green light and red light, depending on the specific transition and altitude. Nitrogen, molecular nitrogen, and nitrogen ions contributes blue and purple hues, especially at lower altitudes where collisions are more frequent and energy states change more quickly. This is why auroras can look like a painter's palette that has been diluted into the sky. The colours are not arbitrary, they're a clue. Each hue is a signature of which molecules were excited, how much energy was delivered, and where in the atmosphere the collisions occurred. But the aurora is not just colour, it's shape, curtains, arcs, rays, swirls, sudden brightening that feels like a silent crescendo. So now, quietly, we turn from what to how. Imagine you are looking at a city at night from above. You see roads and neighbourhoods as patterns of light. The aurora is like that, but the roads are magnetic field lines, and the neighbourhoods are regions of particle precipitation. The light you see is not up there in the way the moon is up there. It is spread through a volume, through a layer, and your eye compresses that layer into a two-dimensional impression. Curtains happen when the emission is structured in thin sheets aligned with magnetic field lines, and your line of sight turns those sheets into rippling folds. Rays happen when you see fine scale variations along the direction of the magnetic field. Arcs happen when the precipitation region forms a long, relatively narrow band that can stretch east-west across the sky. And then there are the subtler forms, diffuse aurora, a broad glow without sharp edges, like a dimmer turned up across a wide area. Pulsating aurora, which looks like patches of light gently blinking, brightening and fading on timescales of seconds. The aurora can be a sharp signature or a soft ambience. It can be a line or a wash. None of this requires myth to be beautiful. The physics is sufficient. Still, we can acknowledge something without letting it steer the case. Humans have always noticed these lights, and they have always told stories about them. That's what people do when the sky behaves like a living thing. But tonight we're keeping our hands on the instrument panel. If we mention the old stories, it will be the way you might keep a newspaper clipping in the folder. Context, not mechanism. Because the mechanism is already astonishing enough. Let's go back out of the atmosphere and into the magnetosphere for a moment, because this is where the aurora is decided, not in the last collision, but in the long preparation. Energy from the solar wind can be stored in the magnetotail. The tail is stretched by the solar wind's flow, like fabric pulled taut. Under the right conditions, the system enters a phase where energy accumulates. Then, suddenly, it releases. This is one of the ways auroral substorms occur, a cycle of growth expansion, and recovery in auroral activity. In my office, this would be the difference between a day of calm inbox sorting and a moment when the phone rings and a whole set of decisions has to happen at once. The building's wiring and circuits can handle it, up to a point, but the surge forces the system to route energy quickly, and the visible manifestation down in the atmosphere is the aurora brightening and shifting. When people describe the aurora as dancing, they are not wrong. They are simply describing a fast-moving boundary in a system that is reorganizing itself. And that brings us to one of the most useful ideas for gentle understanding. The aurora is a footprint. It is the footprint of currents and particles and fields. It is a map of a process you cannot see directly. And like any footprint, it tells you about what passed through, how heavy it was, how fast it moved, and where it came from. So, if we want to understand the aurora, we can treat it as evidence. The colours tell us something about altitude and composition. The shapes tell us something about how precipitation is structured and how field lines guide motion. The timing tells us something about how the magnetosphere is being driven and how it releases stored energy. Now, before we go deeper, let's pause in the room for a moment. I let my eyes rest on the folders tab, Northern Lights, and below it, in smaller letters, Aurora Borealis. The office hum holds steady, like a reminder that systems can be calm even when they're doing constant work. The lamplight pools on the desk, warm, limited, controlled. This is the right mood for space physics, because space physics is not loud, it is precise. We can proceed with the chain in order, like a well-run investigation. First link, the solar wind. The solar wind is a plasma, an ionized gas of electrons and ions. It streams outward from the sun and carries the sun's magnetic field with it, stretched into a spiral by the sun's rotation. The properties of that flow, its speed, density, temperature, and magnetic field orientation, change over time. Those changes matter because the magnetosphere responds differently depending on the conditions. If you've ever heard that a southward-oriented interplanetary magnetic field is favourable for geomagnetic activity, what that's hinting at is geometry. When the solar wind's magnetic field points in a direction that can more easily connect with Earth's field on the day side, reconnection can be more effective. Energy coupling increases. The system is driven harder. Second link, the magnetosphere as a boundary. The magnetosphere is not a rigid shell. It has layers and regions and dynamic boundaries. The day side has a boundary called the magnetopause, the surface where the pressure from the solar wind balances the pressure from Earth's magnetic field. Upstream of that boundary is the bow shock, where the solar wind slows and becomes turbulent as it encounters Earth's obstacle. Downstream, within the magnetosphere, the flow and field organize into regions, the day side, the tail lobes, the plasma sheet, and more. This is not trivia. These regions are where energy is stored and released, where particles are accelerated, where currents form. It is the architecture of the case. Third link, pathways along field lines. Once particles are energized and directed, they can travel along magnetic field lines into the polar upper atmosphere. These are often described as precipitating particles. They come in from above, guided, not random. They deposit energy through collisions. Fourth link, the atmosphere as light emitter. The upper atmosphere is thin but not empty. When energetic electrons collide with oxygen and nitrogen, they excite them. Those excited atoms and molecules emit light as they relax. The dominant colours depend on the species and altitude. Green aurora is common because oxygen emissions in the green are efficient at the altitudes where aurora often deposits energy. Red aurora tends to occur at higher altitudes where oxygen can emit red light without being collisionally quenched too quickly. Blue and purple hues arise more readily from nitrogen emissions, often at lower altitudes where higher energy precipitation can penetrate. If this feels like a lot of moving parts, that's because it is, but it's also repetitive in a comforting way. The system runs the same logic again and again. Inputs vary, outputs vary, the chain remains. Now, let's slow down and take each piece with more care and more imagery, without letting the imagery become vague. Picture the Earth at night, from a place where you can see the whole hemisphere. You see a curve of darkness. You see city lights, where humans have replaced the night with their own grid. And then, near the polar regions, you see a soft ring of glow, sometimes faint, sometimes bright, like a crown that doesn't sit perfectly still. That ring is the auroral oval. The oval exists because the mapping between the magnetosphere and the ionosphere is not uniform. Field lines that connect to certain regions of the magnetotail and magnetosphere intersect the atmosphere at high latitudes. When particles travel along those field lines, their precipitation occurs in the oval. When geomagnetic activity increases, the oval expands. In practical terms, that means the precipitation region moves to lower magnetic latitudes. The crown grows. This expansion is one of the reasons auroras are associated with space weather. It is not only an aesthetic event, it is a marker that the magnetosphere-ionosphere system is being driven strongly enough to rearrange currents and particle distributions. Those currents have names. You don't need to memorize them for sleep, but it helps to know they exist. There are field-aligned currents, sometimes called Birkeland currents, that connect the magnetosphere to the ionosphere. There are horizontal currents in the ionosphere, including auroral electrojets that flow around the polar region. These currents can change rapidly during active periods. And rapid changes in magnetic fields are exactly the kind of thing that can induce currents in long conductors, like power lines down on the ground. So the aurora is not just a light show. It's evidence that currents are moving and changing in a way that can matter for technology. But we don't need to escalate. We can be calm and factual. Most auroral activity is mild. The system is built for it. Earth has been doing this since long before there were power grids. Our job is simply to understand what it is and where our modern systems intersect with it. Now, there is a question that always comes up, often in a whisper. Why does the aurora appear to move? Part of the answer is that the precipitation regions themselves can move as the magnetosphere reorganizes. Boundaries shift. Field-aligned currents change. The oval can brighten on one side and fade on another. Substorms can trigger rapid expansions and poleward motions of auroral arcs. Part of the answer is perspective. The aurora is spread through a volume. As the structure changes within that volume, your eye sees it as motion across a two-dimensional dome. And part of the answer is that the aurora is coupled to waves and instabilities in plasma, patterns that are inherently dynamic. A magnetized plasma is not a still medium. It is lively, even when it is quiet. So the aurora dances because the system is alive with electromagnetic structure. Let's put that in office terms, since we're using the office as our metaphor. In a well-run office, most days are routine. Mail arrives, files are sorted, decisions are made at a measured pace. But sometimes, a priority case drops on the desk. The routine flow changes. People move between rooms. Conversations happen in parallel. The hallway fills, briefly, with motion. That's like a substorm. Not chaos, but reconfiguration. The system doing a lot of work in a short period. And even on a routine day, An office is never truly still. Electricity hums, air moves through vents, computers process, clocks tick. The aurora has an equivalent background: steady solar wind, steady magnetospheric convection, steady coupling that can produce faint auroral glow even without dramatic storms. If you live far from the poles, you might only think of auroras as rare events. But in the polar regions, auroral activity is a regular feature of the environment. Now, let's take a gentle detour into the colours, because colour is one of the most satisfying parts of the case. It is beauty that comes with labels. When an oxygen atom emits green light in the aurora, it is typically emitting at a specific wavelength, one that corresponds to a specific energy transition. The famous green aurora line is around 557.7 nanometers. Red aurora is often associated with oxygen emission around 630.0 nanometers. These are not arbitrary. They are quantized signatures. Nature's barcodes. The reason green is so common is partly because of where the energy deposition often happens, roughly around 100 to 150 kilometers, though the altitude can vary. At those altitudes, oxygen emissions can produce bright green. Red emissions from oxygen tend to come from higher altitudes, often above about 200 kilometers, and sometimes well above 300 kilometers, where the atmosphere is thinner and excited oxygen has time to emit red photons before being de-excited through collisions. Nitrogen plays its own role. Molecular nitrogen and nitrogen ions can emit blue and purple light. These hues often appear at lower altitudes, especially when higher energy particles penetrate deeper. Sometimes you'll see a green arc with a faint purple fringe at the bottom. That can be a clue that different species and different energy deposition profiles are layering the emission. This layering is one reason auroras can look like they have edges and textures. The atmosphere is stratified. The energy deposition is structured. The result is a kind of luminous topography. Now, we should be careful with a common misconception. The aurora is not burning. It is not heat in the way a flame is heat. The air is so thin that even though individual particles are energetic, the total heat content isn't like standing near a fire. It is light emission in a rarefied gas. Another misconception: auroras are not just reflections of sunlight. They are their own emission. They happen at night, not because they require night, but because we require darkness to see them. And now, since we're building this like a case file, we can lay out the timeline of an auroral event in a way that feels like an investigation. You can imagine a day when the solar wind conditions change. Perhaps a stream of faster solar wind catches up to slower wind ahead of it, creating a compressed region. Perhaps a CME arrives, carrying a strong magnetic field and a density enhancement. Perhaps the solar wind's magnetic field turns southward and stays that way for a while. Earth's magnetosphere feels this as pressure and magnetic stress. The day-side boundary shifts. Reconnection can increase. Energy enters the system. The magnetotail can store more energy as it stretches. In the ionosphere, currents respond. The auroral oval can brighten. The oval can expand. The field-aligned currents can intensify, and then, at some point, the stored energy is released, often through reconnection in the magnetotail, accelerating particles and driving a substorm. From the ground, what you see might begin as a faint arc low on the northern horizon. It might hold steady for a while, like a patient line drawn in chalk. Then it might brighten, it might split, it might form rays, it might surge overhead and fill the sky with curtains. And then, gradually, it might fade, leaving only a dim glow. and then the stars. This pattern, quiet build, sudden expansion, slow recovery, is one of the rhythms of auroral activity. Now, there is another rhythm that matters: local time. Auroras are often more active around local midnight in many conditions because of how the magnetosphere and ionosphere couple and how the auroral oval maps. That doesn't mean auroras can't occur earlier or later. They can. But if you're trying to understand why many observers talk about the late evening and midnight hours as prime time, the system's geometry and circulation are part of the answer. Still, in our office, we are not planning a trip. We are studying a system. And systems are more soothing when you understand their regularities. So let's talk about the magnetosphere's circulation, gently, because it explains why the aurora isn't just random. When energy couples into the magnetosphere, it can drive a large-scale flow pattern, plasma convection from the day side toward the night side and back, guided by magnetic fields. The ionosphere, as a conducting layer, participates. Electric fields map along magnetic field lines. Currents close through the ionosphere. This is where the aurora becomes not only a light emission, but a sign of electrodynamics. Particle precipitation and current systems are linked. In many auroral arcs, the precipitation is associated with regions of upward field-aligned current, where electrons are accelerated downward. If that sentence felt too technical, let it soften. All it means is that the aurora is where the system's electrical pathways touch the air. In an office, wires bring power to the lamp. The lamp emits light. In Earth's space environment, field lines and currents bring energy to the upper atmosphere. The atmosphere emits light. The analogy isn't perfect, analogies never are, but it is useful. It keeps the story organised. Now, at this point in the case file, I usually do something that helps me later. I draw a simple diagram in my mind, not with numbers, but with roles. The sun is the supplier. The solar wind is the delivery truck. The interplanetary magnetic field is the orientation of the cargo, how it can connect. The magnetosphere is the receiving dock and the storage warehouse. Reconnection is the process that opens pathways. The magnetotail is the long storage corridor where energy can build. Field lines are the rails for particle motion. The ionosphere is the conducting layer where currents close. The upper atmosphere is the light-emitting screen. And the aurora is the visible receipt. Once you see it this way, the case stops feeling mystical and starts feeling inevitable. Under the right conditions, a star and a planet with a magnetic field will do something like this. And in fact, auroras occur on other worlds too, with their own variations, because the underlying ingredients can exist elsewhere. But Earth's aurora is our subject tonight, and it has its own signature: oxygen green, oxygen red, nitrogen blue, oval geometry, storms and substorms, coupling and currents, and the quiet reality that our technology is now part of the environment that the aurora is signalling. So, we should spend some time on the question of space weather impacts, not to alarm, but to complete the picture. When geomagnetic activity is strong, the changing currents in the ionosphere and magnetosphere change Earth's magnetic field at the surface. Far below the aurora, those changes can induce currents in long conductors. That is one route to geomagnetically induced currents in power systems. In the upper atmosphere, increased particle precipitation and electric fields can change ionospheric density and structure. Radio waves that rely on the ionosphere, like certain high-frequency communications, can be affected. Navigation systems that depend on signals passing through the ionosphere, like GNSS, can experience errors when the ionosphere is disturbed. In space, satellites can be exposed to enhanced energetic particles and charging environments. The very process that paints the aurora can also populate regions of space with particles that matter to electronics. Again, most of the time, the system is within manageable bounds. But it is part of why we study the aurora, because it is visible evidence of a coupled system that has practical consequences. And now we've arrived at one of my favourite parts of any scientific case: how we know. Because you might reasonably ask, if so much of this happens invisibly, fields, particles, reconnection, how can we possibly speak about it with confidence? The answer is that we measure what we can in multiple ways, and we build a consistent story across instruments. On the ground, we use all sky cameras to capture the aurora's shape and motion. We use spectrometers to measure the aurora's emission lines, which tell us which atoms and molecules are emitting, and sometimes allow inference of energy deposition. We use magnetometers to measure changes in Earth's magnetic field, which are signatures of currents in the ionosphere and magnetosphere. In space, we place spacecraft upstream in the solar wind to measure its speed, density, and magnetic field before it reaches Earth. We place spacecraft in the magnetosphere and magnetotail to measure fields and particles and to observe reconnection directly. Missions like those designed to study reconnection have provided detailed observations of the microphysics in regions where field lines break and reconnect. When you combine these measurements, solar wind monitors, magnetospheric probes, ground cameras, magnetometer networks, you can correlate changes. A solar wind change arrives, magnetospheric boundaries respond, currents change, aurora brightens. The chain becomes empirical. In the office metaphor, this is like having logs: door access logs, network traffic logs, power consumption meters, temperature sensors, CCTV in the hallway. If something happens, you don't guess. You check the records. Space physics is full of records, even if they are measured in nanoteslas and electron volts rather than in receipts and timestamps. Now, because we're making this episode for sleep, we'll keep the tone gentle. But I want to give you something soothingly concrete. A slow walk through a typical auroral journey from the sun to the sky, told like a quiet narrative. Imagine the solar wind as a river flowing past a rock. The rock is Earth's magnetosphere. The river cannot pass through it easily. It flows around. It piles up pressure on the upstream side and creates a wake downstream. In the wake, the magnetotail, field lines are stretched, and plasma collects. The system is not static. It is always adjusting. Sometimes, as conditions in the river change, the wake changes. Eddies form, energy builds, and then, in a moment of release, the system rearranges. Energy is converted. Particles are accelerated. Those particles spiral along field lines like beads on threads toward the poles. They enter the thin upper atmosphere and collide with oxygen and nitrogen. Excited atoms and molecules relax. Photons are emitted. And you, standing on the ground, see a glow that looks like a living curtain. All of that happens without sound. But it is not silent in the physical sense. The plasma is full of waves, the currents are moving, the system is humming as surely as my office hums with electricity and air. Sometimes people ask if the aurora makes audible sound. There are reports and debates and anecdotes. But in our folder tonight, we don't need the sound to appreciate the mechanism. The visible evidence is enough. Now, I want to slow down further and do something that tends to relax the mind. Define boundaries. In a case file, boundaries are everything. Where does one system end and another begin? What counts as inside? What counts as outside? What can cross the boundary and what cannot? The magnetopause is a boundary. It's not a wall. It is a surface where pressures balance. It shifts. It ripples. It can reconnect with the solar wind's field. It can let energy in. The ionosphere is a boundary too. It's a conducting layer that sits between the neutral atmosphere and the space environment. It is influenced by solar radiation from above and by particle precipitation and electric fields from the magnetosphere and by winds from below. It is a mediator, and the aurora occurs at the interface where precipitating particles deposit energy in the neutral atmosphere. It is a boundary phenomenon like many beautiful things in nature. Waves break at the shoreline, clouds form at condensation thresholds, lightning strikes along electric field boundaries, and auroras glow along magnetic and atmospheric boundaries. If you find that kind of pattern soothing, you're not alone. The universe loves boundaries. They are where structure happens. Now, before we continue, I want to offer a small, gentle permission. You don't have to hold all these terms in your head. You don't have to keep track of every layer. If you remember only the chain, sun, magnetosphere, field lines, atmosphere, light, you will have the essence. Everything else is texture. And texture is what we can add now, slowly, like turning a file into a story. Let's talk about why auroras tend to be seen in certain geographic regions, because it's a practical question and a scientific one. Auroras are centered around the magnetic poles, not the geographic poles. Earth's magnetic axis is tilted relative to its rotation axis, and it drifts over time. So the auroral oval maps to magnetic latitude. That's why certain places, Alaska, northern Canada, Scandinavia, are famously good for auroral viewing. They sit under the usual position of the oval. But because the oval expands during storms, the aurora can be seen at lower latitudes during strong events. This is not because the particles suddenly reach farther. It's because the mapping of where precipitation occurs shifts. The system's footprint grows. Now, what about the difference between the northern lights and the southern lights? In principle, the aurora exists in both hemispheres, around both magnetic poles, because field lines connect north and south. But the auroras are not always symmetric. Differences in the magnetic field, seasonal illumination, and the details of coupling can produce asymmetries. Observationally, fewer people see the southern lights simply because fewer people live at high southern latitudes and because geography makes access harder. But the physics is shared. Two polar footprints of one global system. Now, I can feel the case file trying to split into two parallel narratives, the big global magnetosphere story and the intimate, local, what you see in the sky story. So let's braid them. That is often the most calming way to handle complexity. Braid rather than stack. When the magnetosphere is strongly driven, the aurora brightens and becomes more dynamic. That's the global to local link. When the aurora changes colour and shape, it tells you about altitude and energy deposition. That's the local to global clue. A bright, structured arc might suggest relatively discrete precipitation associated with strong field-aligned currents. A broad, diffuse glow might suggest a more spread-out precipitation region and different particle populations. Pulsating patches might reflect wave-particle interactions, modulating precipitation. None of this requires you to be a specialist. It simply requires you to treat the aurora as evidence and to accept that evidence can be layered. Now, another question people ask, often because it's comforting to ask, why does the aurora happen more at solar maximum? Solar activity follows a cycle, roughly 11 years in its sunspot count rhythm, though the details vary. During more active periods, the sun produces more eruptions and stronger variations in the solar wind, statistically. That increases the chance of geomagnetic storms that can drive bright auroras and expand the oval. But auroras can occur at any point in the cycle. Long-lived coronal holes can produce high-speed solar wind streams that drive recurrent geomagnetic activity even outside of solar maximum conditions. The system has multiple ways to be energized. So if you've ever seen a quiet headline saying, "Auroras possible tonight," it might not be a dramatic CME. It could be a persistent stream and a favorable magnetic orientation. Again, not a single switch. Conditions. Now, I want to return to the office metaphor because it's the spine of this episode, and I don't want it to drift away. In my office, the hum is the baseline. The aurora has a baseline too, the constant solar wind and Earth's steady field. The folder is the case. It contains the chain and the clues. The desk lamp is localized energy conversion, electrical power into light. The aurora is also localized energy conversion, particle energy into light. The office window is a boundary between inside and outside. The magnetopause is a boundary too. The office has rules: what comes in, what stays out, where documents go. The magnetosphere has rules too. Field lines guide particles, reconnection opens pathways, currents close through the ionosphere. And the most satisfying part, the office is built to maintain balance: air, temperature, power, time. Earth's magnetosphere is also a system of balance: pressure balance, energy balance, current closure, particle population cycling. So, as the night goes on, we can keep returning to that sense of calm system management. The aurora is not chaos, it is operation. Now, we're going to do a long, slow tour through the magnetosphere's rooms because it will make later auroral behavior feel more intuitive. Picture the day side first. The solar wind flows toward Earth. It meets the bow shock, where the flow is slowed and heated and made more turbulent. Downstream of that is the magnetosheath, a region of shocked solar wind plasma that flows around the magnetosphere. Then comes the magnetopause, the boundary where Earth's magnetic field becomes dominant. Inside, closer to Earth, the field is stronger. The inner magnetosphere contains regions where charged particles are trapped and drift, including the radiation belts. Farther out, on the night side, the field lines are pulled into the magnetotail, which has two tail lobes, north and south, separated by a central plasma sheet. The plasma sheet is important because it contains hotter, denser plasma and is a region where reconnection and particle acceleration can occur, particularly during substorms. When reconnection occurs in the tail, it can produce flows and dipolarization, a change toward a more dipole-like field configuration closer to Earth, as energy is released. If you imagine the magnetotail as a long corridor with shelves of stored energy, reconnection is the event where a door opens and energy flows through. The system reorganizes, and the aurora responds. Now, because we're here to sleep, I want to turn this into a slow sensory image. I imagine the magnetotail as a dark hallway stretching behind Earth, not empty, but full of motion you can't see, full of tension in invisible lines. Most of the time, it is stable enough, just long and quiet. But sometimes it snaps into a new arrangement, not violently, but decisively, like a filing cabinet drawer that finally slides into the right groove after resisting. When that reconfiguration happens, the aurora brightens. The hallway's change has a footprint in the sky. Now, we're going to return to the atmosphere because we've earned it. When those accelerated electrons reach the upper atmosphere, they collide with oxygen and nitrogen. The collisions occur in a region where the air density is low enough that the particles can travel significant distances before colliding, but high enough that collisions still happen frequently enough to produce visible emission. The details of energy deposition matter. Higher energy electrons can penetrate to lower altitudes before losing their energy. Lower energy electrons deposit their energy higher up. This contributes to the vertical structure and the colour layering. This is why the aurora can look like it has a green middle with a red top and a bluish fringe, because different emission processes dominate at different altitudes. Now, I want to be careful and honest. The aurora's colours are not always cleanly separated. The human eye in low light also perceives colour differently. Rods and cones respond differently in darkness. Cameras can capture colours and faint structures that eyes might not register the same way. So part of the aurora's colour story is physics, and part is perception. But the emission lines are real. The atoms emit what they emit. The physics is the foundation. Now, we can talk about a kind of aurora that is easy to overlook: diffuse aurora. Diffuse aurora is often a broad glow, less structured. It can fill large parts of the sky and can be more common than dramatic curtains in some conditions. It often relates to particle populations and scattering processes in the magnetosphere that produce widespread precipitation. In the office metaphor, diffuse aurora is like the building's ambient lighting, not one lamp turned on sharply, but a general illumination that tells you the system is active. Discrete aurora, by contrast, is like a desk lamp switched on and aimed, structured, localized, bright. And then pulsating aurora is like a light that gently flickers with a rhythm you can almost count, often due to modulation by waves that affect how particles scatter into the atmosphere. These distinctions matter because they remind us that the aurora is not one thing. It is a family of phenomena with related causes. Now, let's address another question that can keep people awake if we don't answer it calmly. Can the aurora be predicted? We can forecast conditions that make auroras more likely. We can monitor the solar wind. We can estimate geomagnetic activity indices. We can model the oval's likely extent. But the aurora is a coupled system with variability and thresholds. Timing and exact forms are not fully deterministic from a human observer's perspective. In other words, we can know the environment is favourable, but not promise a curtain at 11:17 p.m. over one particular lake. That uncertainty isn't failure, it's honest physics. The system is complex, and some of its triggers are sensitive to details. In the office, you can predict you'll get mail tomorrow. You can't predict the exact minute a particular envelope hits your desk, especially if it depends on traffic, sorting, and internal routing. The aurora is like that, but with plasma. Now, since we're being thorough, I want to fold in the ionosphere more explicitly, because it's the layer that quietly does a lot of the work. The ionosphere is created largely by solar ultraviolet and X-ray radiation ionizing the upper atmosphere during the day. At night, ionization can decrease as recombination occurs, but the ionosphere remains, and it can be modified by particle precipitation and by electric fields mapped from the magnetosphere. During geomagnetic disturbances, ionospheric density structures can become more complicated. That matters for radio propagation and navigation signals, because those signals interact with the ionosphere. So the aurora is linked to ionospheric variability. The glowing parts are just the most visible part of a broader electrodynamic response. Now, we've been focused on electrons because electron aurora is the common and visually striking one. But there are also proton auroras, where precipitating protons contribute to emissions. The mechanisms and signatures differ, and often proton auroras are studied with specific instruments and wavelengths. We don't need to go deep into that tonight, but it's worth noting because it reminds us again, the aurora is a family, not a single member. Now, let's take a moment to breathe in the story as a whole, because we've collected many clues. The sun produces the solar wind. The solar wind carries magnetic fields. Earth has a magnetic field that creates a magnetosphere. Energy transfer is enhanced under certain magnetic orientations and conditions. Reconnection enables energy and particle acceleration. Particles are guided along magnetic field lines. They precipitate into the upper atmosphere near the poles. Collisions excite oxygen and nitrogen. Those gases emit light as they relax. The aurora is the visible result. If you hold that chain in your mind, the rest of the episode can be allowed to drift through you like a calm tide of detail. And now, I want to do something that the best case files always do. Zoom in on one night and follow it minute by minute, as if we were sitting in the dark waiting, not with impatience, but with the steady attention of someone who likes the slow accumulation of evidence. Imagine the sky is clear, the stars are visible, the moon is either absent or not too bright. The horizon is dark. At first, there may be nothing, or there may be a faint milky band low in the north, a suggestion rather than a statement. It could be mistaken for a thin cloud, except it holds a shape that feels too deliberate. That faint band is an arc. An arc is often the first structured thing you see. It can sit there for long minutes, sometimes longer, holding steady in a way that feels almost artificial. Then it brightens. The green intensifies. The arc develops texture. Rays appear, like the teeth of a comb, vertical streaks that seem to stand in place and yet shift subtly as you watch. If the event is stronger, the arc may surge. It may break into multiple arcs. It may expand overhead. The whole sky may become a dome of moving curtains. If you were watching with an all-sky camera, you would see patterns you can't easily see with the eye's narrow field of view. You would see the oval structures sweeping across. If you were watching with a magnetometer network, you might see changes corresponding to enhanced currents, signatures of the substorm. If you were in space, you might see the magnetotail reconfigure, flows and field changes tied to reconnection. All of these are different perspectives on the same story. And then, eventually, the bright activity subsides. The curtains become fainter, the arcs retreat, the sky returns to stars. The aurora is ephemeral because it is a dynamic response. It is not a fixed object. It is an event. Now, if you're still awake, I'm going to offer one of the most calming things science can offer, a sense of scale. The aurora may feel like it is close because it fills the sky, but it is high above you, often around 100 kilometers or more. That's far enough that you could drive for hours without reaching the place the light is being emitted overhead. It is not a local street lamp. It is a vast region of the upper atmosphere participating in a global system. At the same time, the structures in the aurora can be fine. Thin rays and folds can represent narrow regions of precipitation and current. So the aurora is both vast and detailed. That combination is part of its power. Now, the case file also includes a gentle caution about interpretation. Cameras can make auroras look brighter and more colourful than they appear to the human eye. Long exposures gather photons. They reveal faint reds and purples that your night-adapted vision might not see as strongly. That doesn't mean the camera is lying. It means it is measuring light with a different integration time than your eyes. In science, that's not a problem. It's a feature. It lets us quantify and compare. Now, because we're here for sleep, I'm going to shift the pacing slightly. We're going to do a slow inventory of auroral forms, each one like a piece of evidence laid gently on the desk. An arc, a long band of light, often oriented east-west. It can be stable for minutes. It can be the quiet beginning. A curtain, an arc with folds, like fabric rippling, often showing vertical structure. Curtains can move and shimmer. Rays, vertical streaks aligned with magnetic field lines, sometimes appearing as fine comb-like structures. Diffuse glow, a broad illumination without sharp edges, often filling large areas. Patches, localized regions that can brighten and fade. Pulsating aurora, patches or bands that brighten and dim periodically, often with a gentle rhythm. Coronas, when rays converge overhead due to perspective, making it look like a burst from a central point. Each of these forms is not just a shape, it is a clue about how particles are being accelerated, guided, and deposited. Now, you might wonder, what accelerates the electrons? How do they become fast-moving enough to excite atoms? There are multiple mechanisms. Electric fields aligned with magnetic field lines can accelerate electrons downward. Wave-particle interactions can scatter particles into loss cones, paths that lead into the atmosphere. Reconnection can energize particles and create flows and fields that lead to acceleration. The details can be advanced, and we don't need to solve every microphysical puzzle tonight. But the key is, electrons do not simply drift in lazily. They are energized by the system's electrodynamics. Now, as the night continues, I take my pen and write one line in the margin of the folder, the way I always do when I want to make the case memorable. The aurora is the atmosphere acting as a screen for space weather. It is the Sun-Earth connection made visible. Now, we can proceed to the final part of the file, how humans engage with it scientifically and what it teaches. One of the most beautiful things about auroral science is how it forces you to use multiple vantage points. If you only watch the sky, you get the visible forms, but not the upstream causes. If you only measure the solar wind, you know what arrived, but not exactly how Earth responded. If you only study the magnetosphere, you see reconnection and particle populations, but not the atmospheric emission. So the field becomes naturally interdisciplinary, naturally collaborative. Networks of instruments, ground and space, modelling and observation. The system demands a wide view. And because it demands a wide view, it makes for a particularly soothing kind of learning. You can float between perspectives without needing to grip any single one too tightly. Now, I want to bring us gently toward a close. But before I do, I'm going to give you 3 seamless extension sections. If you paste them in where indicated, the full runtime comfortably reaches about 75 minutes in most calm narrations. They're written in the same voice, with transitions that stitch smoothly. If you'd rather keep the episode shorter, you can skip them without breaking the story. Extension Section A. Insert after the paragraph that ends with, "The aurora brightens. The hallway's change has a footprint in the sky." Now, let me open a smaller envelope inside the larger case file, because it contains a map of the building itself. When we say magnetosphere, we're naming the whole structure. But the structure is made of rooms with different rules. And when you understand the rooms, you begin to understand why auroras can look different from night to night, even under the same broad label of active or quiet. Closest to Earth, the magnetic field is strongest and most dipole-like. In that region, charged particles can become trapped and drift around the planet, forming belts of energetic particles. Farther out, the field weakens and the solar wind's influence grows. boundaries become more dynamic. Particle populations become more varied. On the day side, the magnetopause is the boundary you can imagine most easily, the place where the solar wind pushes in and Earth's field pushes back. But it's not a hard surface. It ripples and flutters like a flag in a steady wind. And sometimes, under the right magnetic orientation, it reconnects, creating channels where energy can enter. On the night side, the magnetotail has two lobes, regions of relatively strong magnetic field and lower plasma density, separated by the plasma sheet, which is a region of hotter, denser plasma. The plasma sheet is like a corridor with traffic and turbulence. It is a place where the magnetic field can change configuration during substorms, and where reconnection can occur, releasing energy stored in the tail. If you want a gentle image, picture the magnetotail as a long, dim library wing behind Earth. The lobes are tall shelves lining either side, orderly, structured, quiet. The plasma sheet is the walkway down the centre, where things move, where decisions happen, where a sudden rearrangement can send a ripple through the whole building. When reconnection occurs in the tail, it can create jets of plasma that rush earthward and tailward, as if the system has opened a valve. Closer to Earth, the magnetic field can snap back toward a more dipolar shape, a reconfiguration that is tied to the auroral brightening and expansion you see from the ground. This is why the aurora can feel sudden. It isn't because the atmosphere suddenly decided to glow. It's because the magnetosphere decided, through physics, not intention, to release stored energy in a different pattern. And this is also why auroral science often talks about coupling. The solar wind and magnetosphere couple through boundary processes. The magnetosphere and ionosphere couple through field-aligned currents and mapped electric fields. The ionosphere and neutral atmosphere couple through collisions and winds. It's a stack of couplers, each one transferring energy and momentum across a boundary. And when the couplers are active, the aurora appears, like the building's indicator light, glowing not to entertain, but because the system is doing work. Extension section B, insert after the paragraph, that ends with each of these forms is not just a shape, it is a clue about how particles are being accelerated, guided, and deposited. Sometimes, to understand a clue, you have to understand the language it's written in. Auroral light is written in spectral lines, and those lines are not only pretty, they're diagnostic. They're how we confirm which species are emitting and under what conditions, and how we separate what we think we're seeing from what is actually happening. Oxygen's green and red emissions are classic because they are strong, and because oxygen is abundant at auroral altitudes. But oxygen has a quirk that matters. Some of its excited states have relatively long lifetimes. That means, at lower altitudes where collisions are frequent, an excited oxygen atom might be knocked out of its excited state by a collision before it has time to emit a photon. In other words, the light can be quenched by collisions. At higher altitudes, where the air is thinner, the excited oxygen has more time to emit light before collisions interfere. That is one reason red aurora is associated with higher altitudes. The environment allows it. This is a quiet, elegant point. The atmosphere is not just a screen, it is part of the rules of the emission. Density matters, collision rate matters, chemistry matters. Nitrogen, too, tells its story. Under strong precipitation, when higher energy electrons reach lower altitudes, nitrogen emissions can become more prominent, producing purples and blues that sometimes appear at the lower edge of a green arc. And when the aurora is extremely intense, the colours can blend and wash out into pale tones, sometimes appearing whitish because multiple emissions overlap, and because the brightness saturates the eye's ability to distinguish. Now, consider the shapes again with this in mind. A thin arc can represent a narrow region where precipitation is concentrated, which often relates to specific current systems and electric fields. The arc's position can shift as the system's mapping changes. Multiple arcs can form when multiple precipitation regions exist in parallel. Curtains and folds can be linked to fine-scale structuring in the precipitation and to the geometry of field lines. Rays often align with the local magnetic field direction, which is why they can appear vertical even as the aurora spreads across the sky. Pulsating aurora is particularly calming to watch because it carries its own rhythm. Scientifically, pulsations are often linked to processes in the magnetosphere that modulate precipitation, including wave-particle interactions that periodically scatter electrons into atmospheric loss cones. The result is a gentle blinking that can feel almost like the system is breathing. And then there is diffuse aurora, which can be pervasive, especially after midnight in some conditions. It can be the background glow that tells you precipitation is widespread, not focused into sharp arcs. In a way, diffuse aurora is the system's ambience, the atmosphere quietly processing a broad drizzle of energy rather than a focused beam. All of this is to say, the aurora isn't one script performed over and over. It's a language with multiple dialects. The grammar is the same: particles, fields, collisions, emission. The sentences vary: arcs, curtains, pulsations, glows. And the more you learn the language, the more the sky feels readable, even as it remains mysterious in its details. Extension section C, insert after the paragraph that ends with "Space physics is full of records, even if they are measured in nanoteslas and electron volts rather than in receipts and timestamps." Sometimes, the most reassuring thing in a complex case is knowing that the evidence is redundant. We don't trust one instrument. We trust patterns that show up across many instruments, each sensitive to a different part of the system. When a spacecraft upstream measures a sudden increase in solar wind speed or density, that tells us the input is changing. When it measures a rotation in the interplanetary magnetic field, that tells us the coupling potential may change. Those are like the delivery notes on the incoming shipment. When magnetometers on the ground measure disturbances, that tells us currents are changing overhead. Networks of magnetometers can even help map where the currents are strongest and how they move. Those are like the building's power meters and circuit monitors. When all sky cameras show arcs brightening and expanding, that tells us where precipitation is occurring and how it evolves in time. When spectrometers measure emission lines, that tells us what species are emitting and can help infer something about the energy and altitude of the emission. Those are like the surveillance cameras and the chemical tests in a lab. When radars probe the ionosphere, measuring electron densities and velocities, they tell us about the conducting layer's response and the electric fields driving it. Those are like the building's airflow sensors and occupancy maps. And when satellites in the magnetosphere measure particle distributions and fields, they give us direct evidence of acceleration regions, reconnection events, and plasma flows. Those are like being able to walk into the hallway behind the scenes and watch the staff moving during a surge. This redundancy is why auroral science can be confident about the broad chain, even when the fine details are still an active area of research. The big picture is consistent across decades of observations: solar wind driving, magnetospheric coupling, particle precipitation, atmospheric emission. And now, the final layer of the file: what this means for living on a planet inside a star's extended atmosphere. The solar wind is part of our environment. It shapes Earth's magnetic boundaries. It drives currents and auroras. Most days, it is a quiet driver. Some days, it is stronger. And because our civilization has built long conductors, sensitive satellites, and navigation systems that rely on signals passing through the ionosphere, we have become more connected to the state of this space environment than any previous generation. Studying auroras is one way we study that environment. They are not the only way, but they are the most poetic way, because they let our eyes witness a process that would otherwise remain hidden. So in a sense, the northern lights are a natural display panel for a physical system. Not a warning light necessarily, not an alarm, just an indicator. The coupling is active, the ledger is moving, the energy is being routed, the atmosphere is paying out light. Now we can close the extensions and return to the main file. Back at my desk, the lamp is still warm. The office hum is still steady. The window is still a dark rectangle of sky. In that darkness, the aurora may or may not be active at this moment, but the system is always there. Fields in place, solar wind flowing, boundaries adjusting, currents ready to form. The machinery of the invisible is operating whether or not we are watching. And that is, in its own way, very calming. Because it means the aurora is not a performance staged for us. It is a process. It is nature doing its accounting. If you remember only one image tonight, let it be this: a stream of charged particles flows outward from the sun. Earth's magnetic field meets it, shapes it, and guides it. Energy enters under certain conditions, is stored and released, and is carried along invisible pathways. And at the end of that chain, high above the ground, oxygen and nitrogen emit light, green, red, blue, turning unseen motion into visible glow. A quiet receipt printed across the night. So, when you imagine the northern lights, you don't have to imagine magic. You can imagine a system, a boundary, a ledger, a lamp in the sky powered by a star and regulated by a planet's magnetic shield. I close the folder gently. The desk lamp keeps its small circle of warmth. The hum keeps its steady note. And the window holds the sky, dark and wide, with room for whatever gentle evidence the night decides to reveal. My name is Madeline Rowe, and this has been the Science of the Northern Lights for Sleep. Good night.